on top of LFE and just look at some ways of implementing them and some effects of them, right? So yeah. Be a bit about LFE, a bit about Lisp Machine Flavors, implementing the flavors, and also implementing flavor instances, the actual objects themselves. We get all that way down, right? So yes. So LFE stands for Lisp Flavored Erlang. It's a Lisp running on the Erlang system. It's a real Lisp with real Lisp syntax. You can see it with real Lisp macros. I mean, macros done correctly, right? Right, they should be. But to run efficiently on the beam, it's been tuned to run on the beam. So it might look Common Lisp-like, but it isn't Common Lisp. So it has the standard Erlang data types. The beam Erlang data types has standard beam Erlang handling of modules. There's no way to get around that if you want to make an efficient system. And a few other things as well. For example, all data is immutable. I mean, there's nothing strange about do that. So just a bit of example code. It looks very Lispy. So this is actually real code, to be honest. It's not just made up for this one. Again, you can recognize a lot here. I'm defining a module, virus here. I'm exporting two functions, start of 0 arguments and start of 1 argument. Then I'm defining the function start here with no arguments and start with 1 argument. Right? Typically, you'll define like you get in Common Lisp for it. This actually works. It starts a virus. So after you've started this, any node that connects to this node will now become infected with a virus. Yeah, it works as well too. And it breaks through everything where you're running distributed Erlang. So yes, the code's about half again as much. So I mean, this is just basic how it looks like. I've got my spawn process here. I have a case where I'm checking the values and doing pattern matching. So pattern matching has been built into the language and things like this for as well. And I can do my other things. I've got access, of course, to all the BIFs and stuff like this. So I can call regist here. So I'm registering the module. My process under that name, I'm calling that kernel here to monitor nodes. I'm writing out you've been infested, and I go into a loop. And basically what the loop does every time the net kernel tells me a node's been connected, I will do some RPC calls, install code into that module, and then call that and infest it. Right? It's about half a page more of code for it. And surprisingly enough, it works. Yeah, so this is just a bit of LFE, just to see what it's like for it. So it is a really very Lispy syntax for the language for it. And as with most Lisps, a lot of things here are macros. So both defun and def module, for example, they're just macros. Okay, so that's the straight bit therefore. The next interesting thing is getting into Lisp Machine Flavors. Okay. So this was an object-oriented system running on the original MIT Lisp machines. It's from the late 70s, so it's a very old system for it. And there was no real final version of it. It just kept developing as time went. So if you look at the documentation, every year there'd be new features in it, right? And eventually it was enormous. They were just basically throwing in everything they could think of for doing things here. We're just going to look at a few bits of it, right? Yeah, it was a precursor to the Common Lisp object system. But I think it's much more fun for it, how it was designed, how they were thinking and things like this for it as well too. The close one was, or is more standard, very big, but I think this one, I personally think this one was much more fun, right? And yeah, so you could define a flavor. So this is pretty much the standard syntax from the Lisp machines, except I've added one thing at the end, an end flavor here saying when it ended. Okay. So I could define a flavor with a flavor name. I could define instance variables. We had components. We'll see more what these are. And for that flavor, I could define methods for it. And I could also make local function definitions I could call within the method. There's nothing really strange at this level for it. So I could give instance variables, and I could give default values for instance variables. And these values, the expressions you gave for the values were then evaluated when you created the instance, not at the time I was defining the flavor or compiling or whatever. These were done when the instance was created. You had a bunch of options. So I implemented some of the options. Some of them were very specific to the machine, but some of them weren't. So the first bunch here, gettable, settable, and initable instance variables, that just defined which of the instance variables I specified up there, the system would auto-generate accessor methods for. Right? So all the gettable instance variables, they would automatically have a get method defined for it. The settables would have both gets and sets. And initable ones, they were the ones I was allowed to initialize, give values for when I created an instance. Otherwise, you weren't allowed to do that, right, by default. So they're pretty straightforward. The next set of required here, that says, okay, I'm making this flavor, I'm connecting it together with components, but for this flavor to be usable, I require that some other flavor I'm mixing it with provides a set of instance variables, or provides a set of methods, or actually requires, adds extra flavors as components. This is just saying, for my flavor to work, to be happy, I need these extra things. Someone else has to fix them for me. That's what that set says, right? There were other things as well. You could give initialization values. You could do default initialization lists and things like this for it as well too. The abstract flavor is slightly different. That says that this flavor can only be used as a mix-in to other flavors. I cannot create an instance of this flavor by itself. And this gets back to how things were combined, how components were used. Right? They didn't call them classes. These were flavors, and I didn't have superclasses. I had components of mixing in. There were other flavors. This just says this flavor can only be used together with something else. I cannot create an instance of this one. So yeah, methods, well, you can define callable methods. There are a couple of different ways of defining methods. We're going to see two of them, or three of them, depending how you want to count it. The default way is I do a def method of a name here with a definition for it, and that's called a primary method. That just defines a method for this. And the definition this would just be standard Lisp LFE definition, which include the arguments and so on for it. So again, seeing we're running on top of LFE, running on top of Erlang, I can have methods with the same name and different number of arguments. They're just different methods. Right? I didn't mention it here. Well, indirectly, when you're running LFE, it's the same as Erlang. You can have functions of the same name and different number of arguments, and they're different functions. This is nothing strange. From the Erlang point of view, it's nothing strange. And yeah, so I could just define methods here. And these were called primary methods. There are other methods as well. We'll see some of them. These are primary methods. Okay. Yeah, and you can define local functions that only exist within this flavor, only accessible from other functions or methods from within that flavor. So it's quite, in that sense, it's quite, I think, so far it's quite a standard package, object-oriented package for it. Now we get into the components. Now we're going to combine these things, right? And so with a flavor, you can give it a list of components. That was if we step back a couple of things here. Here I can give a list of components. This one's there. They can be empty. And this is an ordered list of flavors that this flavor has as components. It will incorporate things from these components. Okay. And the important thing there, it's an ordered list. Okay, for it. The ordering is I've given this sequence of components. They, of course, can have components of themselves and nested things like this for it. And from my point of view, this flavor's point of view, the list of components is the flattened tree of all the components. And this tree is actually an acyclical graph. So you can have components that have other components which incorporate them as well too. So I can have circular list of components here, and this whole thing is just flattened out in a nice way, in a predefined way for it. Okay. This allows me to mix in flavors. So here, these aren't really like classes or superclasses. We're mixing in. I don't know, I tend to think of more like cooking, right? I'm going to make a pot of something, so I want a meat flavour. I'll chuck into my pot, and I'll have some salt flavour and maybe some onions and maybe some things mixing in. It's much more mixing in, and these flavours, of course, they can have other flavours as components. So I can mix in quite complex things, right? I mean, for example, I could mix, if I'm making a curry stew, I could mix in a curry flavour, which is actually composed of a lot of other spice flavours as well too, for it, but not quite as classes in that sense. I can view them as classes if I want to, but they're not. They're much more general. This is what I think was the fun bit about it, to be honest. So what does a component flavour do? Well, it defines instance variables. So a component flavour can have its own instance variables, and what I will see in my flavour, I will just see the union of all the instance variables from all the components. There's nothing strange there. Will defines which methods exist for a flavour, so for my flavour. So I'll incorporate all the methods, the union of all the methods from all the components. But now we run into a slight problem here. So what happens if I incorporate a method, the same method from multiple components, from multiple flavours? I might have defined it, some of my components might have defined it. This is where the ordering comes in. So my flavour is assumed to be the first one in my list of components, but you will step down that ordered list, and for each flavour, if it occurs multiple times, take the first one in that order. So if it occurs, by default, if it occurs multiple times, you take the first one, and that's the one that's used. Okay. Yeah, that means that if I define a method in a flavour, I have no guarantees that if this method's called, my version of the method's the one that's going to be called. So in my food flavour here, I can define a bar method. There's no guarantee that this is the one that's actually going to be used. I might be a component of another flavour which defines its own bar, which means it's going to be used, not mine, right? So I have no difficulty. I have no guarantees that what is actually going to be used and which ones are going to be used. That causes problems, okay, of course. But we have help with daemons to get around this. Okay. So here is a simple example using composition. So I'm defining two flavours here. I'm defining a flavour shape up here, which has got two instance variables, x and y. Now I've said that x and y are settable. That means that they're automatically going to define methods for setting and accessing these instance variables. There's going to be a set x and a set y, and an x and y methods automatically defined here. That's nothing strange here. I define a method here, move_to, which takes a new x and a new y, and I set the values for this instance, the x and y values for this instance, new x and new y. Just return OK. So I have a set form here for setting values of instance variables. I have a relative move_to here, which takes delta x and delta y and bumps up x. So we have a get for getting the values, and I've just bumped these up and set x to that one. And the same thing with y here, and I would OK. And down here I have a draw method, which just writes out some information when I call it, just drawing shape out where it is, where the values are. Nothing strange about that. Okay, so this is one base flavour here, and I can define a circle flavour, which uses shape as a component. So it's going to get all the stuff from components. It's going to get the x and y variables and things like this, and the x and y methods and so on. It's going to inherit move_to and rel move_to, get those as well, but it defines its own draw. So when I create an instance of circle and call draw, I'm going to get this draw. I'm not going to get that draw. We also have our own instance variable radius here. So here we're just two flavours, a base flavour and one incorporating that. Okay, so far nothing strange, right? But here we even see now that this draw is not called because I'm using it inside a circle which has its own draw. Okay. So how do we get around this problem? How can I be certain that for a method, something I want to be done with that method is always done? So far we've seen a can't. I mean, we saw the draw here. This draw will only be used if no flavour using me as a component, or is in a component list of someone else before me, which has defined its own drawer. Okay? And of course, there was a solution to this problem. Well, there is one. It's called daemons. So I can define daemon flavors, or sorry, daemon methods. Yeah, so the sequence of flavor may override a desired method. Right? So we have a foo method, but someone earlier in the component list, a flavor earlier in the component list also has a foo method. And I can't do much about that, because I have no idea how my flavor is going to be used. Right? So we can have daemons do that. And I can create before and after daemons for each method I want to. So I can define a method here as foo, it's a before daemon. Here's a, say, foo and an after daemon, again with definitions, same number of arguments, etc., etc. Now what happens when I define daemons is, so if we have an example here, we'll go there first, then go back. Yeah. So when you're creating the flavor, for each method, you'll create what's called a combined method, which contains the primary method, which is the first one in the list of components, and before and after daemons. So what happens is when I call that method, I'm first going to evaluate all the before daemons for that method, then the primary method, and then the after daemons defined for that method. And the before daemons will be in the ordered list of components, and the after daemons will be in the reverse order. So I can always plug something in here. I might be able to plug in the method, but I can plug in a daemon to make sure so I can get access when things happen. And that's what this example here was. So I'm defining a moving object flavor here with instance variables x, y, and x velocity and y velocity, and default value for those just 0. They're all gettable, so I'm going to get methods, I'm going to get set methods, and I'm just saying these are initable. I can't set the x and y. There's no set function, there's no set method defined for x and y, and they're not initable as well either. But I can define a move to method here, which just sets x to a new x and y to a new y. And I can do a set velocity method here, which takes a new x velocity, a new y velocity, and sets x and y vel to those. That's my moving object flavor. So, but now I'm going to define a snail flavor here. And the thing with a snail is it moves very slowly. So I want to make sure that what I want to do is if someone sets the velocity, I want to make sure that the velocity isn't too fast for my snail. Okay. I don't want a snail going at 100 kilometers an hour, for example. That's slightly above it. So for my snail flavor, I've got two instance variables, max x velocity and max y velocity. That just says that this is the maximum velocity for this snail. That's what I'm thinking about. And it's a moving object. They're all initable, so I can set these when I create them. I won't do that here. The trouble is, I want to get into the set velocity. I want to make sure that the velocity is not too fast, right? Now, if I was to define a set velocity method, there's no guarantee that mine's going to be called. My snail might be together with a moving object or something else which has a set velocity which overrides my set velocity. So how can I get in? Well, I can define an after daemon. So I know that if set velocity method is called, my after daemon will always be called. So now I can go and say, yeah, well, I've got the new x velocity and new y velocity. I'll just ignore those for the time being. I don't need those. But I know that somewhere there is a set velocity method which should set the x velocity and the y velocity instance variables. So now I just check. I just make sure they're not too big. So the x velocity is bigger than max x, well, I'll just set it to that. I'll just set the minimum of them. So now this after daemon, this will always be called. And I know that I will do that after the main method's been called. Now, I hope no one else does another after and does something different. So why not do it as a before? Well, I don't know what the main method does here. So I can call this an after. And I can have before daemons, I can have multiple before daemons. You have long sequences of things going on here before the actual method comes in. And this is a way to allow me, my flavor, always to get in there and do things. If I want to be really safe, for example, I could do both a before daemon and an after daemon, but I don't need that here. And the combined method, that's what's actually called when you call the method, is a combination of the before daemons, the primary method, and the after daemons. This is built up by the system when I do it right. So this is great. If I have this mechanism, I can do things, I can do a lot more. There were a lot more other features as well that came in. For example, you could have, there were ways of combining the primary methods. So I could make a version where I said, I want to call all the primary methods. And maybe do a sequence of AND on them, so if they were true, I would keep calling them, otherwise I would stop and things like this. There were a lot of ways of combining methods. You could define your own combinations as well too. But I think this was enough, at least for this anyway. So yeah. So now how am I going to implement this? Now we get on to the interesting bit, the implementation. So there were a couple of things that they had here as requirements, which I think fit very well. For example, there was no requirement for the order of defining and compiling flavors. So if we go back and look at my snail and my moving object, just because snail used moving object as a component, there was no requirement that moving object should be compiled before snail. Okay. Now the same thing with the shapes. I've got the shape and the circle. There's no requirement that the shape is compiled before circle. And again, this fits very well into normally how Erlang modules work. There's generally no requirement in which order the modules are compiled, just as long as they're there when I actually want to use them. Right? So this is pretty straightforward here. You could, for every flavor, build a set of methods and compilations for every flavor using the combined methods it has. It is difficult to do because you get circular paths around the methods. You have to resolve those. I mean, how they were resolved is very straightforward, very standard, but you have to resolve that. So it can be very difficult to do that for every flavor. And then you also have these abstract flavors which can only be used as mix-in, which you can't use as base flavors. Okay. And that would mean, yeah, so it'd be difficult to do it, keeping track of the component order. It also means, okay, I do my snail, so I compile my snail and I compile in and make something. Then someone else uses snail as a component, which means they have to go compiling in things, and suddenly things change, right? My after daemon is now called, not called when I expected it to be, it was going to be called some other time, for example. So that was very, it's not a good way of doing it. You could do it, but you have to be, it's better to be cunning. We can do round things here. And now we're getting to the interesting bit. So what we can do is, if we look at the definition of a flavor, we can split up in two parts, or logically split up into two parts. So I can define, I call it a static module. I haven't got a good name for it. I can compile all the information that's in this flavor. I can compile all the methods, both the before and after daemons and the primary methods. I can get a lot of information about what's going on in the flavor. I can do that without having to know anything else. So I can compile my primary method without knowing how it's going to be called, if it's going to be called, and the same with the daemons. Okay. So I can do that for every flavor. I can compile those separately up for every flavor. And in that, I can keep track of the instance variables, which options it has, because they're used when you're building stuff later. I can look at the methods. I can look at local functions. I can build up this one module containing all the static stuff, right? And information as well. And then I can make a dynamic module of all this combined data, which I actually use when I want to make an instance. So when I make an instance, I then have to work out, an instance this flavor, what do I actually need from all the other flavors? And then I can build stuff. And then I can build with all the instance variables and all the combined methods. And then I can resolve how all the methods and daemons are going to be called for that instance, or for that base flavor. And that I don't have to do all the time, right? This is where the cunning bit goes in. So the static flavor is only flavor-specific data. It has no interdependence at all between anyone else. I can make that split to make sure that it's just purely local stuff. Like an Erlang module, it's just purely local. So there are no interflavor module dependencies. I can create that and save that at compile time. I can compile up this module, make a beam file of it, and just leave it there. And all the methods, daemons, and all local functions are in this module. Okay. And then, what I call the dynamic one, that contains the things that are specific for that flavor when I look at that flavor. It contains all the combined methods. It contains, so it contains all the combined methods and a bit of data. But that I can create at runtime. Okay? So that's created at runtime. I don't have to save the beam file for it because it's created at runtime. So I dynamically build that module, compile it, and just load the beam straight in. I don't actually create any beam file for it. And that I do the first time, So it's not saved. And that all the code it calls, all the things that do things, they're in the static compiled ones. So the combined methods here call things in the static modules. It's just putting them all together, just bunching them together, right? I can do that afterwards. And that I delay compiling that until the first instance is created for it. So when I create the first instance for a flavor, then I go in and I build a dynamic module for it and compile that and load it in. Okay. And that is very nice because this allows me to compile all the static modules so when I'm building a release and having that code as the standard beam files in the release. And then dynamically, I'll build the other stuff when I need it. It also means I'm only going to do the dynamic modules for the flavors which actually I'm creating instances of, not anyone else for it. Right? So I can compile all the static flavors. I can put all that in the beam file in the release, and I'll do the other stuff when I'm running it. Yes, it needs the compiler to be there, but it's not difficult. So how does this look? It's very straightforward. This is one of the benefits of using Lisp, by the way. It's so easy to generate code. So if you take all the braces and make square brackets out of them, you've got Erlang lists, right? That's literally all it is, right? So I can show you the code afterwards. It's extremely straightforward. So for example, my moving object, I will define a function called moving object flavor core, which is a static one. And here I export a lot of functions. There are a lot of functions that give information about the flavor. I'm only including a couple of them here. So there's a name function. There's a list of components, which case was 0 here. We have primary methods. Well, there's 2 primary methods defined here. There's a set velocity and a move to velocity of 2 arguments. There are no before daemons, and I'm running out of space, so there's no after daemons as well. And there's information about the options, so I can see which are settable, which are gettable, etc. And from that, I can generate methods. I generate one function here I call a primary method. And this contains all the primary methods. So there's a clause for each one, or multiple, depending on how I define the function. So here's a set velocity. It's going to be called here with 3 arguments, which is the name of the method, self, which is a reference to me, and a tuple containing the arguments of the call. And then I go through, and here's the code for it. And I do this for every method. And here, for example, are some of here's the settable. The settable for set x, it's set x itself is tuple value, and things like that does that for it. So I define all the primary methods here, and here's just a general error saying this primary method didn't exist if you happen to call it wrongly. And you do exactly the same thing for the before daemons and the after daemons. So one function containing clauses for all the before daemons and one for the after daemons. Okay. And this I can do at compile time. This is straightforward. And for the snail flavor core, it's exactly the same thing. It's a snail. It has moving objects as components. We see there are no primary methods, no before daemons. There's one after daemon, and here is the after daemon function for defining after daemons. Right? This is basically all it contains. There are more information functions here for getting information out of it. So this I can compile up at compile time. And then when I'm making my instance, then I can define the dynamic module. So this is the dynamic snail module, the snail flavor module here. And it exports a name, it exports instance variables, init keywords, a few other things, component sequence. This is the sequence of components for this flavor. Worked out for all its components and things like flattened out through that. And here we have the combined methods we have, and here we have the combined method function. So here we've got name, we've got instance variables, we've got the component sequence. It just contains the name of the flavor and the function of the module that flavor static is in there for each one of the flavors. There's a predefined vanilla flavor which comes the end, which adds a few extra methods, mainly just for printing stuff out, default printing stuff for it. And here we have the combine method. Combine methods function. Again, for each of the methods, here we're just defining which ones exist. So this saying, yes, we have a tuple here, say we have a set velocity of 2 arguments. It's defined in the moving object method, or sorry, flavor. There are no before daemons, and there's one after daemon in snail. So I just stepped through for all these here. These are all empty here. So here we see some coming from vanilla, and here's an init to start up and a terminate when you kill a method, just add as well too. And then there's a combined method function here for all the combined methods. So here, for example, we start this one, we have the move to, which has no before daemons, and that just, it knows, it would look in here and see that the move to is in moving object, so it would call moving object the primary method with move to set, that should be self and args there. Come on, stuck, yes. The set velocity, that has a daemon. So there are no before daemons, so we're going to call the primary method, and then we're going to call the after daemon. And the prog one just means we just throw away the return value of the after daemon here. So this could, in sequence, be a number of before methods, before, primary, after. That just builds that up at runtime to do that. And then there's an error saying I'll try to call this with method doesn't exist, I'll just get an undefined error there. So this is the code I generate when I create the first instance. And I just run this straight into the compiler. It generates a binary. I never write out the beam file. I just load that binary into the system, and now I have it defined in here. So that's how it works. Right? So it's great. It works for it. The next problem we're just going to look at is okay, so now I can compile up all my flavors. I can get all the combinations right. There are more options, and I can add more options as well to it. But now we're going to look at the next problem. How am I going to implement an object instance for it? So what's a good way of doing this in an Erlang system, or a bad way? Processes are one way, but if you look at the characteristics of an instance, there's a number of things. How are they handled? What's the weight of it? How much does it cost to have an instance? How do I access it? Is it shareable or not? Right. Persistence. Does it go away by itself? Is it garbage collected? Will they go away by themselves? And what happens if I get an error in it, etc.? And if you look at the data, looking at this definition of the code in the modules, all you actually need in the flavor instance is a link saying what flavor it is, where the flavor module is, and the instance variables. That's all really an instance has to be, because everything else is in the modules. The actions in the modules. And we're going to look at 3 alternatives for it. And the first one, well, it's a process. That would one way be your standard way of doing it. It's a process. It's very straightforward. It's shareable. The reference is just the PID. I can share that and anyone can access it. It's more classic OO instance-like. And it's handled by reference. So I can just pass this thing around for it. This is what I actually use in the current implementation. However, it's not automatically reclaimed. It doesn't behave like data. It behaves like a process, which means I have to kill it to get rid of it. Explicitly kill it, it won't go away by itself, which is not quite what you expect by objects if objects are data, right? It's heavier than classic OO instances. Most object-oriented systems assume very lightweight objects. I might be wrong here, but I think they do. And it's very difficult with recursive access. So if I do a send, which is a synchronous send to an instance, and it sends to another, so I send to instance A, and it sends a request to instance B, which sends back a request to instance A, the system hangs. Because they're in deadlock sitting, they're synchronous, they're waiting for replies to each other. Now you can make it simple to make a hack, so if I call myself, I will not send messages to myself, that's easy. But I have no way of getting around this. It's very difficult to get around this fact that I can get systems blocking. And unfortunately, it can be very difficult to detect this. So if I'm using someone else's flavor with someone else's methods, I have no idea what they're going to do, right? So it's very difficult to do. That's definitely a problem. Again, this is nothing specific here. It's very specific. As soon as you have Erlang processes, you get this problem. So, yeah. So this is what I did, and each instance is just a process. It's a gen server. Nothing strange about this. We're using there's an init and a terminate method, so we're using the gen server's init and terminate callbacks to implement those. That's straightforward. Instance variables, I just keep those in a map, and I put them in the process dictionary. This process is just doing one instance, so there's no problems there. And what I decided here was, well, to make it look like I'm doing something locally, if an error occurs in the instance process, the error is sent back to the caller, and you get an error at the caller. I don't know if that's good or not, but it was fun to do it. So you get functions look something like this. So I'm going in and doing Erlang get of instance variables. You get the date, and then I'm just doing a map on that, which also means I get an error if it doesn't exist. And here in the set, I do get the update, I get the map, and I do a map update, which means if the instance variable doesn't exist, I get an error, which is good. Right? And then I just set it and return the value. So that's one way of doing it. A second way, of course, is to use data structures. I could use a data structure for it. It's very straightforward. It's just, well, a map or something like this. It's very lightweight. It's automatically reclaimed because the garbage collector will collect it when I get back. It's the same idea as Erlang records and Elixir structs. It's like having Elixir. It's like having records and structs on super steroids, right? So I'm not just giving you functions to access the fields. You can do things with them. Right? But unfortunately, it's not shareable. I have this thing, right? I can't give it to someone else. Well, I can, but if they do things with it, I'll never see the results for it. It's just an Erlang data structure. I have to manage it explicitly by the caller. The caller has to pass it into the method call. That's no problem. But when it gets back from the method call, it's going to get both the return value of the method and the updated instance. So I have to carry these things around with me. It's not very classic Go instance-like, right? But it's easy to do it. So you just make a map. Again, you make a map of these things. You put all the instance variables in there and some information about the modules and stuff like this. I could do a transformation. If I have set and get, if I leave the get and set functions for accessing the instance variables, I could do a transformation of the code which automatically chains the self through the code and updates it and passes out the value at the end. It's not too difficult to make that transformation. But the caller must explicitly handle this. So they must do send ref do it 42, and they're going to get back a value and the new reference, which they then have to take care of and pass the new reference down. Again, this is just straight Erlang handling of data structures. The get and the set, well, get is just a maps get, and the set is a tuple will return the value, which is definition of the return value, and we've updated this the map. That's fine. But none of them seem really nice, right? So we would like something shareable, lightweight like OO, handled by reference. We have one, but it's not automatically reclaimed. But you have to be very, I think here we're getting overly cunning. But you can do it, you can do it. And how do we do it? ETS tables. We have a shared ETS table, which is perfectly feasible to do this. I have a shared ETS table, and each, do this for it. Now, how do I handle a shared ETS table so that that ETS table doesn't go away when something crashes? Well, you just make the init process 0, the owner of it. It inherits it. That process, if that process dies, the whole system dies. So it doesn't make any difference. I've done this. It works. So how do you implement it? Well, you store instance variables in a global ETS table flavors instances, and the table is a bag, where the key is a reference to the instance. And each element has to form the instance, the reference to the instance, the variable name and the value for that. And then get is just does a match on this, and does a match on that with the self, the var, and the $0. It gets back that value and it returns that value. If the value is not there, this is going to fail, so you're going to get an error. You're not going to get back the one element list. And the set just puts that thing back in. And it's a bag, so if it's already there, it's going to overwrite it, right? So this works. It doesn't delete itself. You'll have to delete it, but it's quite flat. I don't know. This might be too cunning. I have no idea. But it's perfectly doable. You do exactly the same transformations for the code, for example, for doing things. So yeah, that was basically it. So yeah, I just want to say, yes, you can do these things. If you want object orientation, that's a completely different question, but there are a number of ways of doing it reasonably well and getting the desired reasonably nice handling of it as well too. And I think the handling of the classes, or the flavors in this case, is a very nice way of doing things for it. Okay, now I'm done.
So we have a little time for questions.
Okay.
Does anyone have questions?
Yes, okay.
Thanks, Robert. I
Yeah.
really enjoyed the talk. I just have, when you're describing the 3 different options,
Yeah.
I couldn't help but thinking that like this might be easier if there were some mutable or like shared memory in Erlang. I mean, I guess CTS table is close, but
no.
Okay.
No. Okay, I know that if you're going to start doing things like that, it's going to affect everything else, right? It'll
Could
be
you say something about the Erlang AST? Did I hear you say that? Or you said the Lisp
generating the Lisp code is very straightforward. And generating them as an Erlang structure is basically building the lists. So what I mean is, in the compiler, it's very easy to build this code.
I'm just familiar with the Elixir AST. I was wondering if there's something.
The Lisp syntax is much simpler. You can do it with Elixir. You could do it with using quotes and unquotes, but it suddenly becomes much more complex. You could do it with the Erlang AST as well too, if you wanted to. I just thought this was easier, which it is. I can show you the code afterwards if you want to. And by the way, it works, which is even nice as well too. Yes.
All right. Thank you all. We've run out of time for questions. The light
Okay. Yeah. You can get on GitHub, by the way, as usual.